This is the first in a series of videos about free energy, specifically Gibbs free energy, and how that relates to spontaneity of a reaction. So we're going to derive where this cool new variable Gibbs free energy comes from, as the origin of this was the goal of predicting the spontaneous direction of a process. Okay, so we're looking to talk about spontaneity. So in the last video, we talked about the second law of thermodynamics, and we said that we did know something about spontaneous processes. We said spontaneous processes have a change in entropy of the universe greater than 0. There's always going to be a positive universal change in entropy. And we wrote that out like this. So we said that the delta S for the universe equals the delta S for the system plus the delta S for the surroundings. And this is all very fine and good, but I'm not sure if you've ever tried to measure the entropy, but it is not a difficult thing to measure, especially if you have to measure it for your coffee mug plus the entire known universe. So it is a bit difficult to measure the change in entropy for the entire known universe. So it would be really cool if we could write a formula that did not involve this number so that it was a actually useful relationship. So let's try substituting something else. So we'll keep delta S of the system because we can measure things for the system fairly easily. Let's bring back the other relationship we had for delta S of the surroundings. We said delta S was also equal to Q over T. And it's Q of the surroundings because this is the surroundings term. Okay, and one piece of information that we used in the last video is we said we know that Q of surroundings is equal and opposite to the Q of the system, because that's how we define them. So let's substitute that. So delta S of the system plus negative Q of the system over temperature. Okay, so now we've got all of our variables in terms of system, but we can even do one better. In the enthalpy chapter, we said we cared the most about constant pressure systems because this is how most benchtop reactions occur. And at constant pressure, the heat was equal to the enthalpy change specifically. So let's throw that in there. So delta S of the system minus change in enthalpy over temperature. And that equals delta S of the universe. So now this is starting to look helpful. Now we're relating our champion delta S of the universe to some actual measurable numbers, but we don't really like having temperature on the bottom. So let's go one step further, and let's multiply both sides by negative T, just to move that T up to the top. It'll look nicer that way. So multiply both sides by negative T and rearrange so it looks nice. So we are going to end up with negative T times delta S of the universe equals, and I'm going to swap these terms. I'm going to put this one first. We multiplied by negative T, so this is just delta H. And then we took delta S and we multiplied by negative T, so it's now minus T delta S. And both of these guys, delta H and delta S, are for the system. All right, so this is looking helpful. We've now got delta S of the universe, our indicator of spontaneity, and we've related it to enthalpy, entropy, and temperature. So we're feeling good. Delta S of the universe, that's our spontaneity indicator. And so because this term over on the left side has our spontaneity indicator in it, Mr. Gibbs decided that he was going to use this variable as a predictor. And so he named it after himself, delta G, or Gibbs Free Energy. So Gibbs Free Energy is related to enthalpy, temperature, and entropy. Delta G equals delta H minus T delta S. And at this point, we stop writing of the system and we just write it like this. And this is one of the most important formulas that you will encounter in thermodynamics. And because of that, it has to have a dopey acronym to help you remember it. So the dopey acronym that I was taught as a Lawrence student is Guppies hate tartar sauce. There were no promises that these were going to be reasonable. This is a Lorentz tradition. Delta G equals delta H minus T delta H. T delta S, Guppies hate tartar sauce. And don't forget, the equal sign goes here between Guppies and hate is a negative feeling. So this is going to be a minus sign, minus T delta S. Okay, and so now let's think about what this formula means in terms of words and less in terms of math. So here, delta H, we know about this. We've talked the most about that so far. So delta H is the heat energy, which could be given off or taken in, depending on the direction of the heat flow. But this is the heat energy. This is the total, the maximum energy that we have to work with. Then this term over here, this is the reordering energy. Right, we had this much energy to work with, but we had to spend some of it to reorganize the particles in the system for this change. And so delta G is the energy that's left. It's the useful energy that's available or free to do work. That's getting a little close. So when we call this Gibbs free energy, we don't mean that it doesn't have a cost, because it absolutely does. We had to pay out this T delta S term to reorder to be able to afford it, but it's free because that's the energy that's available to do work in the system. So now we have the ultimate tool for predicting spontaneity, Gibbs free energy. And in the next video, we will talk about the sign of Gibbs free energy and how that tells us whether something is spontaneous or not.